All right, guys, in this section, we're going to be covering hearing or the sensation of audition. So, we're going to be talking about the physical stimulus for hearing first, just like we did for vision. We're going to talk about the anatomy of the ear and then different types of deafness. So the physical sound or the physical stimulus that we actually detect is sound waves. Sound waves have different amplitudes and frequencies, just like we have amplitude and wavelength for color and for brightness. It's the same idea with the waves for hearing. Amplitude is encoded as loudness as or intensity, just like it is brightness for vision. And then frequency is encoded as pitch, just like we would kind of see wavelength as being color. Frequency is pitch, so higher pitches and lower pitches. Most sounds we hear are complex combinations of waves. When you're listening to me talk, you're actually hearing a bunch of different pitches kind of melded together. The only time you really hear a single pitch is with tuning forks. You probably have seen those before. They're like little metal two tonged forks, and someone hits it with another metal piece, and then like they have pure vibrations of a single tone. But generally, what we're hearing in the outside world is combinations of different pitches and different wavelengths. When we look at different types of hearing across the animal kingdom, we actually see that a lot of other animals, just like with vision, have different ranges of hearing. So the human range is like this blue area. This isn't the greatest graph, I'm sorry, but the blue area is what we humans can generally hear. If we look at dogs, they can go actually to pitches that are higher than what we can hear, which is why if you've ever seen like those dog whistles, they don't really sound like a whole lot or just a really high pitched whistle, but dogs are really tuned to them. Um, Other ones that are kind of note, insects go quite a bit beyond our hearing. Dolphins especially, they actually communicate a whole lot in pitches and frequencies that we can't hear. They're much higher than us. And of course, bats, they use high-pitch echolocation to locate food and obstacles in their environment, which is really, really cool. Other animals can go lower than us. Elephants can communicate with really low sounds, and low sounds they travel a long distance more easily than higher pitched sounds. So elephants will actually do these low rumbly noises that, again, we can't hear without specialized equipment. They can communicate over really long distances to different groups of elephants. Same thing happens with whales. They can communicate across really long distances in the ocean. And these lower pitches actually travel really well in water. So whales can communicate over several hundred, if not 1,000 miles, so essentially like a whale can be in Boston and talking to a whale over in Spain and be like, hey, what are you doing over there? They can communicate back and forth with these low pitches, which is really cool. Now, the bad thing about that is the ocean has become really noisy since the invention, essentially, of the steam engine. Because, of course, boat engines make a lot of noise. So boat traffic can disrupt animal communication below the water, just like it can, airplane noises or car noises above water. They also can be disrupted by sonar and drilling and explosions underwater that are done for industrial purposes. So whales have been actually known to be really disrupted by human activity. If you've ever seen whales who have beached themselves, one of the prevailing theories is that they can be so when like the Navy or other like oil exploration groups are going out, they to like say find oil, they will go out and they will use these huge sonic blasts to essentially reverberate that sound into the earth and see where pockets of oil might lie. But in doing so, it's a diffuse sound. It doesn't just go straight into the ground. They're doing it, usually from the surface of the water or some depth down. That sound can impact animals for hundreds of miles around that. And so essentially what they're doing is blowing out their ears. And if whales get their ears blown out, it hurts their navigation abilities. It hurts, it just physically hurts. But essentially does traumatic brain damage to them. And so they think that might be one of the reasons that they'll beach themselves. Other different things like volcanoes and earthquakes actually make a lot of really low rumbling noises, which is one of the reasons why a lot of animals will react when earthquakes are about to happen or they'll leave the area before a volcanic explosion because they can sense and hear these vibrations before we can. Um, it's actually pretty interesting. I mean, if you ever see animals like all leaving an area all at once, better pay attention to them. They probably know something's going to happen that we have no idea about. So any sound above the range of human hearing is considered an ultrasound, and infrasounds are below the range of human hearing. Just like we saw with the light spectrum, parts of the auditory spectrum are outside of our range. We just don't detect them without specialized equipment. Ultrasound stimuli occur at frequencies above the range of human hearing, which begins around 20,000 hertz. You probably have heard of ultrasounds before. They can use it to clean jewelry since these micro vibrations can bust up dirt and debris off of metals. They can use it to clean your teeth. And they also will use ultrasounds to produce non-invasive medical images. If you've ever seen like a woman who's pregnant getting an ultrasound done on her belly, or maybe you've had one done on some of your organs, like I've had it done on my thyroid and I've had it done on my gallbladder. What they're doing is they're using that little wand, and the gel helps conduct the sound, but the sound vibrates through your body and then bounces back to that wand and helps pick up and then make a picture from that. Just like ultrasounds could be used for echolocation with bats. Essentially, we're using the same idea, just we're using equipment instead of our brains, which is pretty darn cool. Infrasounds refers to sound frequencies below the range of human hearing or less than 20 hertz. Many animals, including elephants and marine mammals, can use infrasound for communication. Infrasound is particularly effective in water as it allows sound to travel for very long distances. And humans, though, some governments will use infrasound like speakers, and they will produce nausea, dizziness, and uncontrolled bowel movements, and just other unpleasant symptoms, and they'll use it as a non-lethal crowd control. So if they're trying to break up a riot or a protest, they can pump these infrasounds towards the crowd, and it will break it up because people don't feel well. It's kind of like, if you've ever been in a car with a really heavy bass, maybe some of your friends or older siblings have used those, and maybe like you kind of feel like that feeling in your stomach and like in your heart. That's, bass is a really low sound. So imagine being lower than that and super loud. It's going to make you feel really crappy. So you're going to want to move out of that area. So that's what they'll use for non-lethal crowd control. All right, so just like we did for the eye, I want to go through the anatomy of the ear. The ear is actually broken down into three parts. We have the outer ear, the middle ear, and the inner ear. The outer ear we're going to start with first. That contains your ear itself, an outward ear that you can, touch and feel. It's technically called your pinna. The pinna is made of cartilage and tissue, so it holds its shape, but it's still soft. Just like your nose, the tip of your nose is made of cartilage, so is your ear. You may have some piercings or, things going on there. Just inside that, we get the ear canal or the auditory canal. That's where, a bug could get stuck or you have earwax buildup. If you use Q-tips carefully, that's going into your auditory canal. Now, quick note about ear Q-tips. Q-tips actually shouldn't be used in your ears. If you read the packaging, it tells you not to use them in your ear. If you listen to any doctor, they'll tell you not to use them in your ear. What can happen is that when you're using the Q-tip, it actually can impact wax and debris closer to your eardrum, which you don't want to do. They say if you're trying to dry your ears, put your fingers at the end of the cotton swab part of it, not down the stick, but up near the end of the cotton, and only go in that far as your fingers will allow you to go from that point. And that'll help you kind of maintain a safe way of using Q-tips. So be careful with those. Of course, we have bone all around our eardrum, going with our skull. And then we get to our eardrum. This is technically known as your tympanic membrane. So tympanic, you've probably heard of a timpani drum. It's a big drum that's used in orchestras. So tympanic, it means like vibration. So you have your tympanic membrane or your eardrum. And that is what distinguishes your outer ear from your middle ear. So your outer ear goes from your pinna to your tympanic membrane. Then we have our tympanic membrane that begins on the inside of it is your middle ear, and then that goes all the way to what we call our oval window. And in this space, we have what's most important, these three little bones. These are called ossicles. 1, 2, and 3. We're going to talk about these a little bit more in a second with the different names. We also have our eustachian tube. This actually drains fluid and there's usually filled with air down into your throat. So if you plug your nose gently and kind of blow out, you'll feel like a popping in your ear, and that's your eustachian tube clearing. So you ever do scuba diving or you go down and deep into a pool or snorkeling, you have to plug your nose a little bit and allow those tubes to clear, and that's your eustachian tube right there. If you get ear infections, or you did as a child, that's an infection and inflammation of this area here. It can be caused by a blockage, because as you're a child, it's more horizontal, but as you get older, it becomes more vertical, so it's easier to drain. So typically, ear infections stop around age 5. If you've ever had tubes put in your ear, that's actually where the tubes were being placed, is in your eustachian tube to open these up. So that's probably something you probably felt before. If you get a cold, that can get clogged up, and it makes flying really painful. It just can make it hard for you to hear. So that's what's going on there. Okay, so going back to the ossicles. So the ossicles react when the tympanic membrane is moved. And so sound waves come in, it goes through our auditory canal, and then it vibrates this tympanic membrane. So it goes in and out. And then when it goes in and out, this is like a lever system here. And these will kind of wiggle back and forth in response to the vibrations on the tympanic membrane. That in turn will wiggle this part here. This is called the stapes, and we'll wiggle this little, so this is in between, we're going to go into the cochlea here, this blue thing from here, and there's this little window where these two connect, the oval window. And then, so that wiggling then wiggles this window right here. And now we're into our inner ear. So again, that oval window breaks our inner ear, or from the middle ear. And this blue thing is our cochlea. Cochlea means snail in Greek, and if you look at it, it looks like a snail. We're going to be talking about these structures over here later on, but these are for balance. And if you ever get car sick, you can blame these things, but we'll get to those later on. But the cochlea here is what actually is going to take those vibrations and then transduce that into electrical impulses, which then connect to our auditory nerve, which goes back into our brain. So we're going to talk about this quite a bit more. All right, so let's just kind of go through this again. So our outer ear consists of the structures that are visible outside the body. You could use a scope to kind of see your auditory canal. The outside is the pinna. This is our outer visible structure of the ear. It helps focus and collect the sound like a funnel. If you didn't have these interesting folds and like this flappy tissue that is your pinna, it'd be harder for you to localize where sounds are coming from. So like to know which direction the sound's coming from. You also wouldn't hear as well because this helps collect and focus that sound. The sounds are collected by the pinna and they're channeled into the auditory canal, which ends at our tympanic membrane, also known as the eardrum, and that's our boundary between the outer and the middle ear. All right, these are big slides. Just bear with me. All right, so our middle ear, so the boundary between the outer and the middle ear is formed by the tympanic membrane. We just talked about that. And then the boundary between the middle and inner ear is formed by another membrane, which is called our oval window. Inside the middle ear, we have the ossicles. These are the three tiny little bones. They occupy the gap between the tympanic membrane and the oval window. Generally, these bones are referred to as the malleus, the incus, and the stapes. That stands for the hammer, anvil, and stirrup. If you look at them, that's kind of what they look like. They're the smallest bones in the body, the three of them. I believe the stapes is the smallest of the three, and I think that's the only one that hasn't been injured in a ski accident, last I heard. It'd be pretty tough to break that bone because it is really tucked into your skull. The purpose of the ossicles is to amplify sound energy as it's transferred from the air of the outer and the middle ear to the fluid found inside your inner ear. We'll talk about that in a little bit. Sound waves are weakened as they move from air to water. So you have the air in your auditory canal. And that air with the sound waves is wiggling your tympanic membrane. That in turn is wiggling these bones back and forth. But then when you get to the oval window, inside the cochlea there's water. Everywhere else is air. And of course, water is denser than air. So you have to somehow amplify that. And so those bones, by wiggling back and forth, they're helping amplify those little waves that hit the tympanic membrane, and they amplify them so that when they go to the fluid, it's gonna get enough movement so that it actually can pick up the sound. So without this amplification, we lose a large amount of the sound energy, and we wouldn't be able to hear very well. The inner ear contains the two fluid-filled cavities that are embedded in the bone of the skull. One set is part of the vestibular system, that's like that swirly part, we'll talk about that later on. The other set is the cochlea, again, which is Greek for the word snail, because it's all curled up like a snail shell. It's actually the size of a pea, so it's really small in humans. The cochlea contains specialized receptor cells that respond to vibrations transmitted from the inner ear. So this is kind of what it looks like. So if you were to unroll the cochlea, this thing would normally be all rolled up, but they've unrolled it. The sound comes into this oval window, and as it travels down, different vibrations are picked up by this structure right here in the middle. And these hair cells, when they wiggle, then create electrical currents that go back into our auditory nerve. This is called the basilar membrane, where these little hair cells lie. Now, higher pitched noises are closer to the oval window, and lower pitched sounds are on the other side here. That's why if you did that hearing test, how old are your ears, higher pitched sounds are heard best by younger ears because they haven't had the damage. It's like the first area that gets damaged is these first couple of millimeters. So if you ask your parents to do the same test, they probably wouldn't be able to hear as well. So this damage has occurred for them, and it makes it harder for them to hear these high-pitched noises, but they can still do the low-pitched noises because, again, that's been protected a little bit more. So the cochlea, sound waves vibrate the eardrum. The three tiny bones convert the eardrum's vibrations into the fluid-filled cochlea. So again, we have our eardrum that wiggles these bones, and then those bones can then wiggle the fluid inside here, and that fluid, as it passes across that vibration, then gets picked up by the hair cells of the basilar membrane. So that's what I just said right there. There's an excellent video I'm going to post. It's in the playlist, and it goes through the anatomy of the ear and how it actually works. There's also a crash course video that will cover all this. I really highly suggest you check that out because it's hard to describe without seeing these vibrations actually occurring. So the cochlea is actually divided into three parallel chambers, or kind of stacked one on top of each other. Two of the chambers, the vestibular canal and the tympanic canal, are connected at the apex of the cochlea. That's the really tip of it, the very inside spiral part. And that's the part that's furthest away from the oval window. So that sound has to go down here. This is the apex, and then it comes around here. But again, this is normally all curled up. The vibrations transmitted by the bones of the middle ear to the oval window produce waves in the fluid of the vestibular canal that travel around the apex and back through the tympanic canal. Lying between the vestibular and tympanic canal is a cochlear duct. This cochlear duct is separated by the tympanic membrane by the basilar membrane. So again, we have the first part here, the second part here, and this middle part here is that basilar membrane. Resting on top of the basilar membrane is what's called the organ of Corti, which contains many rows of hair cells that transduce sound energy into neural signals. Each hair cell, or each human ear, has 15,500 of these hair cells. So that's essentially like how many distinct fine pitches are possible for the brain to pick up. Obviously, we probably aren't going to pick up that many fine-tuned pitches, but our ear is that finely tuned that there's 1,500 of these. But again, they begin to be damaged through exposure to really loud noises. All right, so I'm going to go through, we're going to do a quick review. So, out here, what's the outer part there? This here, do you remember, is the pinna. What's this right here? This is the auditory canal. What's this? It's our tympanic membrane. This here, these three here, these are known as the ossicles. This blue part here, it's our cochlea. And this here is the auditory nerve. You don't have to remember much of the rest of the stuff. I just want you to kind of understand this process process of sound waves coming from the environment and then being transmitted into neural impulses going to the brain. All right, so once it hits the auditory nerve, it then goes into the brain and it gets processed first by the medulla, then the midbrain, then the thalamus, and then the temporal lobe. So it has to go into the brain, to the middle, and then brought back out to be processed by the cortex. So just understand that the process takes a few steps before it's going to be processed completely. So the primary auditory cortex is located on the temporal lobe. We've talked about that in chapter 2. That's right behind the ears. The bending of the hair cells will stimulate the release of neurotransmitters onto the cells of the auditory nerve. One branch of each auditory nerve makes contact with the hair cells, while the other branch proceeds to the medulla of the brainstem. So it essentially connects from the ear itself down to the medulla. From the medulla, sound information is sent to the midbrain, which manages reflexive sound responses. So if you have a loud noise, you're going to turn your head. That's that reflexive response. So it has to first go through really low-level processing before higher-level processing. In addition, the midbrain participates in sound localization, so identifying the source of the sound. So is it above you, below you, left, or right? I'm going to put some sound illusions in the playlist for you guys to check out. The primary auditory cortex conducts the first basic analysis of the different wavelengths and amplitudes of incoming information, and then surrounding primary auditory cortex for these areas will do secondary auditory processing and identify things such as clicks, noise, and sounds as having particular patterns, listening to music, listening to speech. Then it gets processed more thoroughly. Here's kind of another image of this. So we have our cochlea, and you can see it now as it's been rolled out, and then you have your oval window where sound comes in from our stapes here. The sound waves essentially get vibrated through this fluid, and then they are going through what's called the perilymph. That's what this fluid's called. It goes down here, and then it comes around, and it goes back through here, and then it actually leaves this little round window, because you can't just have it like clogged up in there. And again, this basilar membrane with little hair cells is right along this middle here. So like I mentioned, damage occurs with age and experience, and a lot of that has to do with loudness of sound. So a whisper, so sound is measured in decibels, and if I was to whisper to you, that's about 20 decibels. So it's very, very quiet. Normal conversation is held around 60 decibels. If you're listening to your iPod or your iPhone, I'm sure you don't have an iPod anymore, your iPad, with the standard earbuds, that goes up to about 100 decibels. And then the threshold for pain is 130 decibels. So if you look at the danger time for the exposure, this is like continuous listening. So at 100 decibels, less than 8 hours of continuous listening can damage your ears. But at 130 decibels, you're in immediate danger. So if you're at a really loud concert, or if you're at an airport and you're like standing next to a jet engine, you're going to begin to feel pain, but then also you're actually damaging those hair cells in your ear, and you won't be able to hear those tones anymore. Pretty much anything above 130 is almost immediate hearing loss, and it's really problematic. This is a problem for people who work on runways at airports. You can see they always wear those really big noise canceling headphones. They also, people who work in factories, people in the military who are exposed to explosions and gunfire, they oftentimes will have hearing loss, and it's really damaging over time because they can't hear a lot of the tones that they normally should be able to hear for their age. When I was finding videos to do that, like how old are your ears test, I was looking for a good one, and I was playing it on my computer, and it was funny because I was like cringing, if you did it, like those high-pitched noises are just awful. And then I had one that I couldn't hear anymore, but my dogs started freaking out. They were looking all over the place, and my father-in-law, who's sitting on the couch around the corner from me, he's like, "What's the problem with the dogs?" And he couldn't hear it at all. He's in his 60s. He's worked on machine floors and factory floors for most of his life, and he has severe hearing loss because of it. He couldn't hear any of the tones except for the lowest one. And then like the ones I couldn't hear, my dogs could hear. They were like looking all over the place, like trying to figure out where that noise is coming from. So it's actually kind of funny that the three levels of our hearing abilities sitting right next to each other. It was kind of fun. So cochlear implants. So people who are born with profound hearing loss or deafness have, on occasion, about 80% of the time, the option to do what's called having a cochlear implant implanted into their brain and into their cochlea. So what this doesn't, it's not implanted in their brain, I'm sorry. It's planted into the cochlea, which then communicates with the brain. So, in a lot of people with deafness, what's going on is the cochlea is malfunctioning. It either doesn't have the hair cells or it doesn't have some sort of functioning component. So, what they do is they put electrodes into the cochlea, which then will stimulate the auditory nerve directly. It actually goes through our eardrum, and there's a little receiver under the skin. There's a quill like right here that kind of sits up behind their ear, and then there's an external part that like magnetizes on, and then there's usually like a wire going down to a microphone, sound processor, battery system, and all that stuff, and kind of hooks around their ear. Now the cochlea can allow people who are born with profound hearing loss or are deaf to hear. Now, the sound isn't as good a quality as our natural hearing. So, like I said, we have 1,500 plus hair cells. They maybe get 150 to 300 hair cells, essentially, or electric signals being put through. So, they're not going to hear the richness of tonality that we can. But it does allow them to, typically, if they're given at a young age, they learn to speak, they can hear music, and they can kind of access the normal auditory environment. So here's a little bit more about it. So like I said, cochlear implants bypass the hair cells and will directly stimulate the auditory nerves. Wires from a microphone carry electrical signals to an external coil. The matching coil under the skin picks up the signals and carries them to one or more areas of the cochlea. This has allowed some formerly deaf persons to hear voices, music, and other high-frequency sounds. About 60% of patients can understand some spoken words and appreciate music. Some deaf children with implants learn to speak. Those who receive a cochlear implant before age 2 have the best chance to learn spoken language at a normal rate. All right, so you're probably thinking like, wow, this is amazing. Like we could almost cure deafness, like 80%, like that's fantastic. The problem with that is just a couple things. So first of all, you're doing a really invasive surgery to typically very young children. So children can't consent to this procedure because they're usually younger than age 2 or 3. So that's one controversy. Cochlear implants, they don't mimic true auditory perception. Like I said, they're not giving the complete range of pitches that you and I can hear. So it's not great. A lot of the early, stories about cochlear implants focus on adults or teenagers who have been given implants and how poor the quality was. But as we've talked about with the brain and plasticity, younger kids are going to have an easier time at this because their brains haven't essentially become, stiffer or less plastic. By the time you're a teenager or an adult getting one of these, your brain's kind of used that auditory cortex for other purposes at that point. You're not going to have the same plasticity. Young kids, you put the cochlear implant in, their brain's going to quickly adapt to that new electrical implant current kind of coming into their brain. A lot of the research shows that, by 2 to 3 years of age, it has to happen, especially for language development. To happen normally, you have to get that implant in as soon as possible. But again, you're doing a very complicated procedure to a young child. Now, there's also a concern with the deaf culture. So I don't know if you know anything about the deaf culture, but people who are deaf, they typically will speak American Sign Language, at least here in the United States, ASL. It's a true language. It's super rich. We're going to talk more about it in Chapter 8 when we get to our language section. But ASL is spoken by deaf people all over the United States. And traditionally, if you had a deaf child, you would send them to a school where they would teach them ASL, a deaf school. And through that, there's become a really tight community of deaf individuals, and they have their own culture. They have different traditions and roles and different kind of ways of navigating the world that allow it to be easier for them in our otherwise sound-rich world. And they have a viewpoint, many people in the deaf community have a viewpoint that cochlear implants are essentially stealing children from the deaf community and essentially forcing them into the hearing community. One of their major concerns is that parents who have children who are deaf or are given cochlear implants, they're not going to learn sign language, and they're going to miss out on the deaf culture. They also, if their cochlear implant malfunctions, or it can't go in water, it has to be taken off certain times, like then they're left without a way to communicate. And that parents and children should always learn ASL if they have a deaf family member. Now, some people have really gone extreme. They, in the deaf community, they'll equate cochlear implants as genocide for the deaf community. But a lot of people kind of take a more middle of the road approach. Kids can be given cochlear implants, but they also should be taught ASL. They should be exposed to the deaf community so they have an option as they get older if they decide that they don't like the cochlear implant or doesn't work for them, and kind of continue to maintain that deaf culture in that deaf community without also maybe making it difficult for children to navigate the general world, because they can't hear. So I want you guys to kind of think about this. I posted a really interesting Vice video about this, and they kind of talk to people who have given their children cochlear implants, as well as people in the deaf community, deaf teachers, and kind of their viewpoints on cochlear implants. So I think you should check that out. It's really interesting to read about this controversy, and I'm curious to hear what you guys think about that. So again, just to remind me to talk about that controversy. And we are all set with this section. In our next section, we're going to be talking about our other sensory systems that don't get quite as much play as vision and audition.